Hi everyone. Today's video is going to cover section 3.1 day 1, and we're going to be talking about the derivative of a function. And what you're going to find as we go through this is that we've actually been doing this already, we've just been calling it something different. So to get started, when we find the instantaneous rate of change for a function at a specific point, we call this value the derivative of the function. Now, hopefully you picked up already, right? We've been talking a lot about this instantaneous rate of change. Now we know that's called the derivative, but I want you to keep in mind this is also what we've been doing when we've been talking about the slope of the tangent. So now we know the instantaneous rate of change, the slope and the tangent, and the derivative are all the same thing. And so when we've been calculating the slope of the tangent, which again now we're calling the derivative, we've been using this formula, which was the limit as h approaches 0 of f of x plus h minus f of x over h. And when we've been finding at a specific point, we've been plugging in a value for x. Okay, so example, if we were finding the slope of the tangent at the point x equals 1, then we would plug in 1 for x. We can still use that formula. However, there's another version of this that I need you to be familiar with that may show up on the AP test. So we're going to look at an alternate version that functions pretty much the same way but looks a little bit different. And so the new formula we're going to be using is the limit as x approaches a of f of x minus f of a over x minus a. And we'll see how that works in the examples that follow. So my first example says to calculate the value of the derivative. Again, remember that is the same as the slope of the tangent. So we're going to calculate that value of the following functions at the given value. So my first example, my function is 1 over x, and my value is x over 2. So we're going to find that derivative by using this formula. My limit as x approaches a of f of x minus f of a over x minus a. And in this case, since my value of x is 2, that's what I'll be plugging in to my formula. So what we're really going to find is the limit as x approaches 2 of f of x minus f of 2 over x minus 2. So in other words, I'm going to make a note here that this is our a value in that function. And so a lot of the work we do to simplify this is going to look as it has in the past. So the same kinds of things we're going to be looking out for. So now again, I'm going to take this work off here so I don't have to keep copying that limit. And now f of x I know is 1 over x. F of 2, if I plug in, is just 1/2. And now I have x minus 2 in my denominator. So now you can see if I scoot this up, sorry about that, that I have a complex fraction. So I'm going to go ahead and kind of kill off those fractions by multiplying the top and bottom by 2x. And remember, this 2x is going to be distributed to both of these terms. And when I do that, when I multiply 2x times 1 over x, I'm going to get 2. And when I distribute to my second term here, I'm going to have minus x. And on the bottom, I have x minus 2, and I have 2x. And so we notice right away we almost have the same thing on top and bottom, but we can't quite cancel it yet. But if I factor a negative 1 out of the top, now my numerator becomes the opposite of x minus 2 over x minus 2 times 2x. My x minus 2's cancel out, and I get a negative 1 over 2x. So now we go back. Remember, we have to take the limit here since we're finding that derivative or slope of the tangent. I'm going to go back up here and I'm going to take the limit as x approaches 2 of negative 1 over 2x. And now my limit rules say I can just plug in 2 and I get a negative 1/4. So that tells me the derivative of f of x equals 1 over x when x equals 2 is negative 1/4. Okay, so let's go ahead and try a second one. So our new function now is f of x equals x squared plus 4. And again, since I'm evaluating this at a specific point, we're going to use our new formula, f of x minus f of a over x minus a. Excuse me. And so now I know I'm evaluating at 1. So I have f of x minus f of 1 over x minus 1. So if I go down here, f of x is x squared plus 4. My f of 1 is going to be 1 squared plus 4 is 5 over x minus 1. And when I simplify this, I'm going to get x squared minus 1 over x minus 1. So now I can see I can factor the top using my difference of squares. So I have an x minus 1 factor in my numerator and my denominator, so I simplify to x plus 1. So now I can go back in and take the limit as x approaches 1 of x plus 1, and my derivative is 2. Okay, so again, we're using this new formula because we're finding the derivative at a specific point. So let's go ahead and flip the page. Now, the difference on this page is instead of finding the derivative at a specific point, we're going to be finding a general derivative. So in other words, I want a formula that's going to tell me the derivative at any point x. I don't want to find it at a specific value. So sometimes, rather than calculating the derivative of a function at a specific point, we want to find a general formula. That we can use to calculate a variety of different derivative values. And so when we're talking about this general derivative, this is exactly the formula that we were practicing with at the end of the last chapter when we were finding the slope of the tangent. So there's nothing new here. Okay, that's going to give us our general derivative. And when we find this general formula, we say that we differentiate the function. So to find the derivative, we have to differentiate the function. So here we see that word. It's going to tell us to differentiate f of x equals x cubed. And then it wants us to use the derivative to find the instantaneous rate of change of the function at x equals 2, x equals 3, and x equals 4. So here's where we're going to use our general formula. Instead of using that specific formula 3 times, we're going to find the general derivative and then just plug into the general derivative to get the derivative at these specific values. So we're going to use our general formula. The limit is h approaches 0 of f of x plus h minus f of x over h. And we're going to be doing the same processes that we've been doing for the last several days here. So now I'm going to plug in to my formula. I'm going to substitute x plus h where I had x. And then I subtract x cubed, and that's all over h. So now I have to deal with this cubed. So I know if I were to square that, I would get x squared plus 2hx plus h squared. And I have to multiply that by another factor of x plus h minus x cubed all over h. And I know this is going to get long, so I'm going to drop down here. So now I'm going to distribute, and I'm going to get x cubed plus 2hx squared plus xh squared. Now I distribute my h's, so I get x squared h plus 2h squared x plus h cubed, and then I'll subtract off my x cubed, and hopefully, as long as I haven't missed anything, we should get things canceling nice and be able to cancel that h in the denominator so that we can take the limit. So I notice I've got my x cubes that cancel. Let's see, I can combine some like terms. I've got a 2hx squared plus an x, no, that's not the right one, plus an x squared h. So I get 3x squared h. And I'm going to cross those off so I keep track of them. Then I've got this h squared x term and another one here. So I got plus 3h squared x. And then I have my h cubed term all over h. And so now I can simplify. And I've got 3x squared plus 3hx plus h squared. So now we need to go back and plug that into our limit. So I have the limit as h approaches 0 of 3x squared plus 3hx plus h squared. And so if I substitute 0 for all of my h's, I get 3x squared. So what we just figured out right there is that our general derivative is 3x squared. And now if I want to find the instantaneous rate of change at these three different values, I can just plug in to my general derivative. So my instantaneous rate of change at x equals 2, I'm going to do 3 times 2 squared, and I get a value of 12. And then similarly, I could just do that for all of my other values. Plug in 3 here, and I get 27. And then at x equals 4, I have 3 times 4 squared, which is 3 times 16, or 48. So the general derivative allows me to calculate a number of derivatives at specific points without repeating that formula 3 different times. So now we're going to move on and talk a little bit about notation, kind of how we represent these derivatives. And there's 3 in the notes, and I'd really add one additional way to this. So there's 4 major ways that you'll probably see notations that mean derivative. And the first is just what we say y prime. Okay, and this notation is good because it's nice and brief, but it doesn't tell us what the independent variable is. The next one we would read as the derivative of y with respect to x. Or a lot of times we'll just say dy dx. Okay, this one's nice because it names both of the variables, and it uses that d to tell us that we're taking that derivative. So we know we have a function y and that the independent variable is x. Okay. The next one we would read the derivative of f at x. Okay, and the nice thing about this one is that it really emphasizes the idea that taking this derivative or differentiation is an operation that's performed on that function. Now, one I would add here, and probably one that you'll see fairly frequently, will look like this. Okay, and we read that as f prime of x. Okay, and what that tells us is that we're taking the derivative of our function x. So f prime of x is another way to say that we're taking that derivative. And really, I would say, of these 4, you'll see these 3 the most frequently. And so as we go through examples, you'll see a lot of times I'll switch up the notation just so we're seeing all the different representations here. So we're going to do 2 more examples. And we're going to go ahead, we're using that definition of a derivative, so our limit definition, to answer the following questions. So now in number 1, we want to find the equation of the line tangent to the curve. So we're actually going to want an equation for our answer. And we know our function is y equals x squared. And we want to find that derivative at the point x sub 0 equals 1. So now we have a little bit of a choice. We have two different formulas for calculating that limit. When I see that it's asking me to find the equation of the tangent line at a specific point, that's where I'm going to go ahead and use my derivative formula for taking the derivative at a specific point. So I'm going to make a note. Since it specified that value, I'm going to find the derivative at that point and probably not use my general formula in that case. So now, I need to find the slope of the tangent, which we now know is also the derivative. So I'm going to use my derivative notation. And so now I'm going to use my specific formula. So I know that's the limit as x approaches, in this case 1, because that's the value I want to find. And I'm going to have f of x minus f of 1 over x minus 1. So again, we're going to go ahead and do our simplification. F of x minus f of 1 over x minus 1 is equal to x squared minus 1 over x minus 1. And this is, again, a fairly easy one to tackle. We can factor our numerator and quickly notice that those factors cancel. So now I'm going to take the limit of my simplified function here, x plus 1, and I know the limit as x approaches 1 of x plus 1 equals 2. So now we've calculated the derivative, which gives us the slope of our tangent. So we have a slope. We know that our point, our x value, is 1. And when I plug that back into my function, I get 1 for my y value as well. So now I can write my equation, which is y minus 1 equals my slope of 2 times x minus 1. And there's the equation of the tangent line for that function. Okay. We'll go ahead and do our last example, number 2. Again, same question here. We're finding the equation for the tangent line. This time our curve is y equals 2 over x, and we're taking it at the point 2, 1. So again, we're looking for the derivative at a specific point. So I'm going to use that formula, especially since it's new and we need the practice working with it. Okay, so now, again, I first need to find the equation of my slope, or the slope of the tangent, excuse me. So again, y prime, that's our derivative, which is our slope. And we're going to use our limit definition. The limit, now we're approaching 2 of f of x minus f of 2 over x minus 2. And we'll work with that a little bit. So now I know that f of x is 2 over x minus f of 2 is just 1 over x minus 2. And so now to get rid of my complex fraction here, all I need to do is multiply by x on top and bottom. Again, I distribute that to both terms. When I distribute it to my first term, the x's cancel and I'm left with 2. And then I have a minus x, and on bottom I have x times x minus 2. Now again, I'm close to canceling here, but they're not exact yet. So I'm going to factor a negative 1 out of my numerator, so that now I have a factor I can cancel on top and bottom. And so I'm left with negative 1 over x. So now to get my slope, I need to take the limit as x approaches 2 of negative 1 over x, and I'm left with a slope of negative 1/2. So now to write our equation of the tangent line, we just plug in. We are already given the x and y value of our point. So now I'm just going to write the equation. Y minus 1 equals negative 1/2 times x minus 2. So that's all we need to cover for today. You guys will get practice during class on Monday working with different problems and deciding whether you should use the general formula or the formula for the derivative at a specific point.